Yes, hello. Is this audible to you people?
Yes, ma'am.
Alright. Okay. So in the last class, we had seen series and parallel combination, and we had also seen mixed grouping. These were the three formula that came out. So in mixed grouping, you have series combination of cells connected in parallel. So series combination combined with parallel combination. So for series combination, current was what? Ne divided by small nr plus capital R. There we had seen two cases. If external resistor is greater than internal resistance, then your current becomes Ne divided by capital R. Secondly, you had what? If your internal resistance, that becomes greater than your external resistance. So small n into R plus capital R, that becomes approximately equal to NR, and your current is E by R. So this is the case for what? This is the case for series. And in case of series, you prefer where your external resistor is greater. So whenever in the question maximum current is asked, then you use this formula. If nothing is mentioned, maximum current is not asked to you people, then first with the help of this, identify whether it is series or parallel combination that you would prefer. And if maximum current is not asked, then use this formula. If maximum current is asked, then we have to use this formula. We did a question also where maximum current wasn't asked, so we used this formula. Second one was parallel combination. In case of parallel combination, EMF remained the same through the R equivalent. We calculated I was equal to M into capital E divided by small m into capital R plus small r, where M is the number of rows. So again, two cases you had where external resistor was greater than your internal resistance. So current became equal to E divided by R. So we are getting lesser amount of current. Then you have small r, which is much greater than capital R. Here you are getting Me by R. Something is getting multiplied to E by R. So hence we prefer parallel combination so as to get more of a current. And then at the last we had seen mixed grouping where M and N represented, M represented the number of rows, N represented number of cells. One small topic that was left on that day that we'll discuss before moving on to magnetics was the heating effect of current. Now, heating effect of current, you people have observed it. Even if you connect your normal mobile phones to a charger, and you leave it for full charging, then after some time you can feel the charger getting hot or the wire that is becoming hot. So that is occurring why? That is occurring due to the current. So what happens basically? See, a resistor is always there. Whenever this current passes through this resistor, some amount of energies you people have studied, you have seen different formula for energy. So what happens, some amount of electrical energy that gets dissipated in the form of heat, and hence we are able to feel the wires or any devices becoming hot. Even after using your laptops, your mobile phones, heating effect you people are able to observe. The reason behind this is this. Best example is your wire. Wire often becomes hot. So let me write this down this way. When current passes through a resistor, part of the electrical energy, is dissipated as heat. This is dissipated as heat. Now see, if I say whatever is the heat that is dissipated for 1 second, for single second, then that quantity which I get, we call it as power. See, power is basically heat Power is equal to heat that is dissipated for 1 second. So heat dissipated per unit time is power. Now few formula of powers are also there. From here you people can see heat will be, if you are asked the formula of heat, remember heat will be equal to what? Heat will simply be equal to power multiplied by time. But what are the formula for power? Formulae for powers include, in case in terms of current and resistance, it is equal to I square R. In terms of potential and resistance, it is equal to V square by R. In terms of potential and current only, without resistance, it is equal to VI. All these are for power. Now, if you see this, this is what? I square R. So heat will be what? Heat will be equal to I square, this I square instead of power multiplied by time. So it becomes I square R. And regarding the SI unit of power, see, power's SI unit will be what? It is heat dissipated per unit time. Heat is 1 joule and second time is 1 second. So joules per second, which is also known as what? Which is represented by capital W. So this topic was left from your previous chapter, that was current electricity. Just note down these points. We'll do a numerical on it as well. First note down these. See, this is the question. An electric bulb has voltage 100 volt, power is 200 watt given. You have to calculate first the resistance of the bulb, then you have to calculate whatever is the power dissipated, but now you have to consider the voltage as 50 volt. So direct formula based questions are there and the calculations are very easy. 100, 250, all the values are easy. Just send the answers of first and second part. Yes, Satif, both the answers are right. This is the answer of first part, Fatma.
Yes, teacher.
Yes, that's right. Correct. Magnitude is right, but Sarah always mentioned the SI unit as well. But yeah, answer is right. Others also respond. Krishna, yes, correct. Krishna's answer is also right. Others, last 2 minutes, then we'll discuss it. Yes, Fatma, answer of second part is also right. Coulomb, correct. 50 ohms is the answer for the first part. Now let's discuss it. Why didn't others try it? Fatima, Munir, Hamza, Hiba, Huzefa. The calculation was very easy for this part. See, resistance will be what? Second one will also be 50 watt. Yes, Sarah, right. 50-50. Both the answers are. Power was what? Power, I've told you, it is V square divided by R. So resistance will be what? Resistance will be V square divided by power. V potential that is given is 100. 100 into 100 because it is 100 square and power is given as 200. So this will be what? 0, 0 getting cancelled. 100 by 2. This is 50 ohms. Second one is what? Power dissipated if it is connected to source of 50 volt. So power is equal to V square divided by R. V now is 50. So that becomes 50 into 50. And resistance, this is given to you. V is given as 50 now. V is given as 50 volts. So this becomes 50 into 50 and your resistance is 50. So your 150 and this 150 gets cancelled. And power also comes out to be 50 watt. These are the two answers. So all those who have not written, just quickly note it down. Then we'll begin with the next chapter. Done. All right. So if few people are done, then let's start with the next chapter. See your chapter number 4 of NCRT, which is moving charges and magnetism. It basically, this is your magnetic effects of current. So in NCRT, this is chapter number 4, which is moving charges and magnetism. Now see, electromagnetism, your first book comprises of electromagnetism. You must have seen EM waves, it is electromagnetism constantly. So electrostatic portions and current electricity part, that has been already covered. Now magnetism, we are moving towards magnetism. Now here understanding of concepts is easier, because you people are aware of most of the concepts of electric field and any concept related to electrostatics. The concept here will be the same, it's just that it will be the magnetic analog of it, but your formulas will be different and the sources will be different. And then we'll be having a combination of both of them, magnetic also and electrostatic also. There you will see you have chapters for it. Electromagnetic induction is there, alternating current is there, electromagnetic waves, all those chapters are there. So even in your 5th chapter, that is magnetism, your 5th chapter number 5 of NCRT, magnetism and matter. In that chapter, you have everything almost related to your electrostatics, whatever you have studied. Like you have dipole moment, then you will be having magnetic dipole moment as well. So you will be, as you have already studied flux, there will be a magnetic flux as well. So everything gets repeated, even axial line, equatorial line, all these topics also get repeated. So that's why keep on revising your electrostatic, because most of the things will be similar to it. Like let's start with this topic, magnetic field. Now, as I've told you people, when we were studying electrostatics, when we studied electric field, what did we study? We studied that every charge, let's say this is some charge, it has a certain space around itself where electrical properties exist, and if we bring a test charge near it, then those electrical environment properties can be felt. Like if I bring a positive charge to this positive charge, then it will repel it. If I bring a negative test charge to this stationary positive source charge, then it will attract it. Similarly, you have the same concept for magnetic field. It is also a space around a magnet. The way in electrostatics, what happened in case of electric field, electric field was the space around the charge. Magnetic field is the space around the magnet. So this is the space around a magnet. Now, in case of electric field, what did we study? Space around the charge where electrical properties existed. Magnetic field is a space around a magnet where its magnetic properties exist. Magnetic properties exist. Now, one major point of difference that will come afterwards also when we study monopoles and dipoles. In charges, you must have never heard of a monopole. No, you have always heard of, in charges you have heard of monopole. Plus Q charge exists, minus Q charge exists independently of each other. We can have a positive Q charge placed, no. So it will be having its existence, it will exist. So monopoles do exist in case of charge. But in case of your magnets, monopoles do not exist. Magnets do not have monopole. Like if this is a north pole, this is a south pole of a magnet. Even if I cut it from the middle, no, this part will develop south polarity and this part will develop north polarity. Monopoles will never exist. It will always have a northern end and a southern end. That is always fixed. So no need to write this. So if this is the north pole, this is the south pole. So what will happen? Magnetic field is what? Magnetic field is basically the space around a magnet where magnetic properties are felt. Magnetic properties are felt means what? If you bring another magnet, then it will attract or repel each other depending upon the polarity of it. And they form closed loop. That those properties of magnetic field lines we'll study the way you have electric field lines. So that's why I'm suggesting you people at least start revising now from bits your electrostatics. You won't either, two things will happen. You won't be forgetting it, and secondly, everything, the concept will be used in your magnetism. So it is the space around the charge where these magnetic properties exist. And again, it begins from the North Pole and it goes and terminates at the South Pole. Begins from the North Pole, terminates at the South Pole. Actually, they do not terminate. Inside, it moves from south to north, but from outside, we are able to see that it begins from the North Pole and it ends at the South Pole. So the way there was electric field, electric strength, intensity, electric flux density, all these topics will be repeated for magnetism also. There will be magnetic field, there will be magnetic field intensity, magnetic flux density, and all those things. Now, representation. This is represented by this symbol, capital B, not M. Do not get confused. Do not take it as M. B, magnetic field is represented by this capital V. And obviously this arrow shows you what? That it's a vector quantity. And the directions, we have specific rules for it. So many rules you must have studied in your lower classes. Fleming's left hand rule and right palm rule, left palm rule, right hand thumb rule. All these many rules are present, which tell you the direction of the magnetic field which is existing. Since we have to have a final combined direction of the magnetic field, now if many number of magnetic field lines exist in any direction, or even if a single magnetic field line exists, we have to have its direction. That's why you have so many rules. So rules we'll study in today's class as well. We try to reach that portion where we study it. So remember that it is a vector quantity. Then the basic point includes the SI unit. So SI unit is Tesla, denoted through capital T. Does anyone have any idea what is the CGS unit of it?
Gauss.
Yes, Atif, right. It's Gauss. Gauss is the CGS unit of magnetic field. Now, 1 Tesla is equal to 10 to the power 4 Gauss. This is an important relation, because when we were studying electric charge, no, we had seen the SI unit of electric charge was Coulomb and CGS unit was electrostatic unit or stat Coulomb. But hardly we have ever used electrostatic Coulomb or any other unit. No, Coulomb is always there. Yes, we can say it might be written as micro Coulomb, pico Coulomb, nano Coulomb. That's different. But Coulomb is mostly used. But in case of magnetic field, you will be seeing Gauss is used. Gauss is used often. So if 1 Gauss you have to convert, then multiply by 10 to the power minus 4. If 1 Tesla is given, then you're converting, then use 10 to the power 4 Gauss. This is a relation that you should remember. This will be used by all of you. In most of the questions you'll see, even for your entrances also. For your entrances, previous years include this relation as well. And in, I think, some of the papers, this has come directly. 1 Tesla is equal to 10 to the power minus 4 Gauss. 1 Tesla is equal to 10 to the power 4 Gauss, and vice versa. This way options were created. So one question was there. Now the next question comes on sources of this magnetic field. What all sources are present, or what are the sources of this magnetic field? See, magnetic field is also generated by a current carrying wire. If you have a wire which is having current moving in a particular direction, that also generates magnetic field. So this is current carrying wire. This was proven by Oysters Experiment. Oysters gave an experiment. I'll tell you that in brief. You don't need to write that experiment. That doesn't come in your exam. But briefly, we'll discuss that experiment also if you people wish. Then obviously it will be a proper magnet. Different types of magnets are there that produces magnetic field. If different types of magnets exist that produce magnetic field, you can have a horseshoe magnet, which is in this shape. Then you have a simple bar magnet. So bar magnets are there. Different types of magnets are there. Horseshoe magnet are there. Bar magnet is this simple bar magnet. Navy blue color or red color, mostly it is available in this color. And then you have horseshoe magnet, which looks in this. This is your horseshoe magnet, and this is your bar. This. So your simple magnets produce magnetic field. Then you have something in your syllabus which you will be studying, where coils are created and a bar magnet is inserted. That creates magnetic field. That device is known as a solenoid. Solenoid. The solenoid is also there in your syllabus. Then do you remember in your chemistry, I think in your 11th class, you people must have done, when you were studying that electron chapter, I think periodic table or what, where you have might have heard of everything when you write about an electron, the valence electron, the number of shell and everything. Then you must have heard of minus half and plus half spin of electrons. Have you heard of? Are you able to recall it? Yes. So yes, that minus half plus half spin of electron. So that also generates magnetic field. Intrinsic, we call it as the intrinsic electronic spin. That is also a source of magnetic field. That's why we write it as either minus half or plus half. One spin does exist in an electron. All right, so these are the sources of magnetic field. For a current carrying wire, let me just tell you in brief, then you people can note down everything. Oysters gave an experiment. So Oysters experiment proved this. basically, what did he do? No, he took a needle. He took a pointing needle. He kept it on a stand. One end of it, one edge of this needle, this was marked with, this was North Pole, this was marked, that represented North Pole, and obviously other one represented South Pole. Then what happened? A circuit was held with proper key was there and a complete circuit. This was the cell, this is the key, these are the wires, and a circuit was there. Now, in this, what happened? Then a galvanometer was attached to it. So, what happened? Whenever the circuit was open, was closed, and the current was allowed to flow. As the current flow, then what happened? The galvanometer showed some deflection. As the current flew, then the galvanometer showed some deflection. Then it was kept beneath it. This north-south pole, how does it show deflection? Basically, north pole initially tilted towards east, then it tilted towards, one time it tilted towards west, then again in one direction this way. And when this whole circuit was stopped, then it was observed that there wasn't any deflection in the needle. So that's how it was proved. Whenever a current was flowing through this, whenever this current was flowing through this, an associated magnetic field also came that deflected the north and south. So this was a small experiment that was done by Oysters, but you don't need to write anything about this experiment in detail. Just make these figures and that's enough. Then we'll begin actually with what are the laws. The way we have studied Coulomb's law, you have Biot Savart law over here. So we'll study this, but I'd suggest you first note down all these points. Done writing this part.
Yes, ma'am.
Then let's start with Savart law. See, difference is that from Coulomb's law, there are many differences and there are similarities as well. But we will not compare it with Coulomb's law because Coulomb's law gives you the magnitude of force. Biot-Savart's law gives you the magnitude of magnetic field. So that's why we'll be comparing it with electric field first. See, suppose you have a wire. A current carrying wire is there. A current carrying wire is there. A current I is flowing through it. I is the current flowing through the wire. Now I have taken a very, very small portion of this current carrying wire. If current is flowing in this direction, then obviously direction of the small element will also be with the same as the direction of current. I call this very small element as current element. The small. So DL is mainly what? This is current element. I have taken a random point P. P point has been chosen. And small r is the vector, position vector. From this P point to the current element. Position vector of what? Position vector of P to this current element. The separation between P point and the current element. So this is position vector of this P point that we have taken. One more thing, one more quantity that we'll define, which is this angle. The angle that is formed between the current element and the position vector. This we are calling it as theta. So theta is what? Theta is the angle between DL. DL is what? Current element, and R. R is what? Position vector. Now let's start with the law. What's the law? All the terms we have already defined. Now let's start. See, according to this law, according to the Biot-Savart's law, according to Biot-Savart's law, your magnetic field, since I have taken a very small portion, no, DL is the smallest portion, infinitesimal small current element that I have taken. That's why I'm taking it as dB. So dB means the magnitude of magnetic field is firstly directly proportional to the current that is flowing through it. This is the first point. Secondly, magnetic field is directly proportional to the current element that is there. Then your magnetic field is directly proportional to the sine of the angle made between DL and R. And lastly, magnitude of magnetic field, this is inversely proportional to R square. Now, if you combine all the four factors, this becomes what? Magnetic field is directly proportional to current element, sine of angle between current element and position vector, and inversely proportional to the position vector. So in Coulomb's law in electrostatics, we had a constant where we used everywhere. Like in electric field, you had seen it was E is equal to KQ by R. K was the constant, whose value was what? 1 by 4 pi epsilon naught. Remember, K is equal to 1 over 4 pi epsilon naught, whose value was 9 into 10 to the power 9. This one. In case of magnetics, you also have a constant. And the value of this constant, the constant in your magnetics, instead of 1 by 4 pi epsilon naught, it is mu naught divided by 4 pi. So this is mu naught divided by 4 pi. Then rest of the terms, IDL sine theta divided by R square. This is your Biot-Savart's law. Now, mu naught is different. Don't get confused or don't take it as epsilon naught. Epsilon naught was absolute permittivity of a medium. Mu naught is absolute permeability of a medium. See, there's a difference. Absolute permeability. This is different. of medium what? When we put not, that shows for free space. So absolute permeability of free space. So basically this shows the effect of a medium on magnetic field. It shows the effect of medium on magnetic field. Whatever is the effect of a medium on different field, that it shows. So Biot-Savart's law shows what? Biot-Savart's law basically shows that your magnetic field is proportional to three things and inversely proportional to r square. This is the Biot-Savart's law. And again, reminding you people, whenever you are doing this, whenever you are writing the derivation, always write the starting storylines. Consider a current element, a current carrying wire with having the current flowing as capital I, current element is DL, and all these things. And if you are running short of time, do mention it at least at the end. What are all these quantities which you have used in your derivation? Otherwise, you will lose your marks. Now, absolute permittivity of free space also has a certain value. Mu naught's value, this is 4 pi multiplied by 10 to the power minus 7. So that's why whenever you have to use the constant, no, 4 mu naught divided by 4 pi, you can write it as 10 to the power minus 7. So mu naught, this is 4 pi into 10 to the power minus 7 Tesla meter per ampere, and it shows the effect of medium on magnetic field. Whatever is the effect of medium on magnetic field. Now, as we discussed, if any other medium was kept, or dielectric medium was kept, or any other medium was kept, then we didn't use epsilon naught. Epsilon naught was specifically for free space. Similarly, mu naught this is also specifically for free space. So the way you had epsilon for any other different medium, then you have mu r, you put mu r, you multiplied with mu naught to write it as it is. So for any other medium, if the medium is changed for any other medium than free space, for any other medium than free space, dB will be written as mu naught multiplied by mu r. Then you have rest of the things, 4 pi here, IDL sine theta divided by r squared. This becomes your. Now let me define mu r as well. This mu r, this is relative permeability of medium. Relative permeability of a medium. So relative permeability, you have this in your syllabus. In your chapter number 5, you have to learn different types of substances. Ferromagnetic substance, diamagnetic substance, different materials are present. So you will be seeing the comparison of all of it. Like if you have ferromagnetic substances there, then value of this relative permeability, this is very much greater than 1. Or if you have a material like iron, then mu r is approximately equal to 1000. The value, the magnitude of it is approximately equal to 1000. Or if you have a diamagnetic substance, then mu r is less than 1. This is the relation. So these relations you don't need to learn right now, you will be seeing. Mu r greater than 1, mu r less than 1, all this is included in your syllabus. You have comparison of mu naught, you have comparison of mu r for different materials that are provided. But right now you are concerned with Biot-Savart's law, which says
so what
that
is the medium of mu naught?
Medium of?
Sorry, not medium, the unit of mu naught.
Mu naught, SI unit, Tesla meter per ampere.
Yeah, okay, thank you.
It's written when you write it down for you. Fine. So others also start writing the points of this law. So from till here you have written no Oysters Experiment. Biot-Savart's law you have to start. All right. See, Biot-Savart's law, if we write it in vector form, normal formula you people have seen, this is dB is equal to mu naught I dl sine theta divided by 4 pi r square. Now, if we write it in vector form, this vector form is not useful. In your calculation, you use the previous one only, but let's not ignore it. Let's write this as well. But in your exams, this is rarely used. If it comes, then you use this formula is there. If you multiply and divide the both the sides by r. Okay, tell me one thing. In which product, cross product or dot product, we use sine theta? Cross product, right? Use it in cross product. So it becomes dl, and see, if we multiply it with r, divided by r and multiply again it with r. So what will be there? dl r sine theta, which can be written as dl cross r. And in case of cross product, remember, if it is dl cross r, then you have to use dl cross r only. Don't replace it with r cross dl. Now, direction of magnetic field, that is very important. See, direction of magnetic field, firstly remember that it is perpendicular to dl and r. This is perpendicular to dl and r vector. Secondly, you must have heard of various rules. But see, for reducing the confusion and for much clarification, we'll use only one rule so that it is standardized in our class. We'll be using right hand thumb. With the help of right hand only, we'll be using different rules for different cases that we'll study as we go through the lesson. But we'll be using this right hand. Otherwise, it at the end, no, it becomes very confusing. You remember, you get confused with all the fingers. Like forefinger represents the magnetic field, or the thumb represents which hand is used if both the hands are involved. So it's better if you use our right hand. Now let's discuss the first method. Method 1. See, in this method, what you have to do, suppose this is a conductor, this is a conducting wire. Wherever is the direction of current flowing, place your thumb accordingly. If I say this is the direction of current that is flowing, then place your thumb like this, in this way. Wherever is the direction of current, place your thumb there. And then you will be having curvature of your fingers. That curvature of your finger, that will give you the magnetic field. Suppose if you put your thumb over here, you will be seeing at this point what is the flow of where your finger curvature is leading, inside the page or towards you, means outside the page. So let me first write the rule before, otherwise then it will get confusing for you people. Hold the wire in right, and yes, do not forget right hand and left hand. Means if you're using, most of the times what happens, students, what they do, most of them are right-handed people, so they are writing with their right hands, and since left hand is free, so not thinking so much, they just put their thumb of their left hand and use it and apply right hand. So be sure, put the pen down and apply your right hand. Thumb points in the direction of current. Wherever is the direction of current, no, right, left, up, down, wherever. So right hand such thumb points in the direction of current. And then the curvature of the fingers points along the magnetic field. the curvatures of the fingers will point along the magnetic field. Like, let me show you this. If this is, suppose this is the wire flowing, this is the wire that is flowing. Let's say current is flowing upwards in this direction, the current is flowing. So your thumb will point here. This is my right hand, I'm using my right hand. So the thumb will be pointing upwards. Now let's say this is my thumb that is pointing upwards. Now this curvature of the fingers, these curvatures, this gives the direction of magnetism. For example, if I choose this point, so my thumb is pointing outward, at this point I will see my fingers are leading inwards. This point, random point I have taken, at this point I'm talking. So curvatures of fingers are where? They are leading inwards. Similarly, you can take any point, you can have different points. So you just have to look at the curvature of finger. Even if your current element is like this, and your current is flowing, let's say in this direction. So take your thumb there, point along it, and then the curvatures of the finger, that gives you the of the magnetic field. So this is what it says: hold the wire in the right hand, and then the thumb points in the direction of current, and that gives you magnetic field. Now let's take some examples on it. Okay, let's say this is one wire. It is pointing in this direction. This one point A, this is B. All of you writing in the chat box the direction of magnetic. See, check whether at A point. First, tell me at least of A point. Whether your fingers are pointing towards you, if their knees are appearing as they are going, as if they are going inside the page, then it will be inwards. So all of you answer me in the chat box. Then only we'll be able to understand this flow. I'll help you. Just answer. I want to know how much correct answers you people give. Then we'll discuss it. I'll explain it again. But try it once. Draw it in your notebook and then try. B. Sarah, what is B? I'm asking you at A point, what is the direction? Inwards, outwards. At B point, what is the direction? Inwards, outwards. Okay, Akifa is right. Fatima, check again. All of you should respond at least. Everyone. Sarah, Kulsum, Krishna, Hiba, Hamza, Atif. Atif, Sarah. Yes, right. Atif, Sarah, Krishna. Akifa, first part is right. Hamza, just check once again. Just check once again. See, is it going outwards or inwards? Just check it. B, Akifa, fine. Okay, Hamza, this is the answer of which part that you're writing?
Ma'am, A.
A part. Others, Fatima, Munir, your answer, did you even try it? Kulsum, A, correct. Hiba, what about you? Hamza, B. Okay, Kulsum, B is right. Hiba, you also try. There's not a single answer from you. And Fatima, Munir as well. Hiba, A. Okay. Now let's discuss this. See, this was the current. Fine. Just place your thumb along the current direction. Fatima, B, what is meant by B? B point is given. You don't have to choose between A and B. What was the question, Fatima? Question was whether magnetic field is going inwards or outwards. If you place your thumb along the screen, if you're using mobile phones or laptops, whatever, then you can place your thumb along it. If you're having difficulties in rotating your device, then what you can do, you can simply draw it in your notebooks. See, place your all those who got outwards as A, those were correct. But people who were getting A as inwards, that was the incorrect answer. A will be outwards if you use your right hand. Sure, you're using your right hand. If you see, just place, if this was, let's say this is the current wire that is flowing. If this is the current wire that is flowing, current is moving outwards. Thumb will be here. Now just check at this point what is happening. Is it going inwards, outwards? See, thumb will be here. Thumb's direction won't be changing. If you keep it like this, if you keep it like this, your nails will point towards that direction where your current is flowing. So if this is the direction of current, at this point you were asked to check. So at this point it will be outwards. At this point, see, this is the curvature of finger. Now if you see the curvature of finger, this is in this way it is moving. So this complete circle is being formed. Now check once again. Keep your finger along the direction of current. All those who were committing errors. Hiba, Hamza, and who was there? I think Fatima, Munir, you were there. Just see all those who got the incorrect answer. Just try it right now. I'll give you one more part because this is very important. If you don't know how to take out the direction, how will you find out the final answer? By just writing the magnitude, it is not sufficient. See, at this point, if I'm able to observe that at A point, my fingers are pointing away, are pointing towards me. Just check, Hamza, just tell me. Put your thumb along the direction of current at A point C. See, when I am putting my thumb in front of my screen, I'm able to see that at this A point, the fingers are pointing towards me. That means out of the page. If they are pointing towards me, that shows out of the page. This shows outwards. And this cross symbol is used for inwards. And towards the screen, like this. This is the curvature of fingers towards the screen. So towards the screen means what? Towards the screen basically means inwards into the page. So inwards or outwards. First try and tell me. Hamza, is this clear?
Yes, ma'am.
Just try it yourself as well. And Hiba, what about you? Hiba?
Yes, ma'am. It's clear.
Okay, Fatima. See, I'm explaining. Fatima, when I'm explaining, do that simultaneously in whichever device you are watching, or in your notebook, even if you have drawn a single line with current pointing outwards, and do it as I'm dictating. Is my voice? Is this audible? Now is this audible?
Yes, ma'am.
Now it's fine. No? Okay. Now Fatima, as I'm saying, do it. Place your thumb wherever the direction of current is there. Just place it like this. This is in your notebook if it is in this manner. If this is your notebook and your wire is like this, then put the thumb in this way. Clear? First point. Now see, at this point A, See the curling of your fingers. Curl your fingers like this. If this is your point A, let's say this is point A, this point is A, then this is my thumb. Curl your fingers. See, if the fingers, the nails, this portion, if the fingers are pointing towards you or they are pointing towards the sheet,
Towards me.
towards you, means outwards of the sheet,
Yes, teacher.
that shows outwards. And similarly, now try it for B point. Place your finger along the current and then curl it at B point. Like suppose this is B point, this is my right hand. So I'll curl it towards B point. See if it is pointing towards you or pointing towards the screen or the sheet.
Towards the screen.
Towards the screen. So it means into the page inwards. That shows inwards. Now this second part you people try. One more direction. You all try. All of you try for A and B. Okay, Krishna, Sarah, Atif, and Hamza. Right answers. So Hamza, is this clear now? No?
Yes, ma'am.
Others also, apart from these 4 students, only 4 students have answered. Okay, Kulsum. Second, B part as well. B is okay. Good, correct. Yes, Fatima. And tried for B part. Hiba, yes, right. Correct. See, it will be like this, no? Now your current is pointing towards downwards. So this is now your thumb. And now if I am using from this side, I don't know in which side it is appearing on your screen, but for me, for my screen, this is the direction of current downwards like this, and A point is here. So if I do it like this, if I curl my fingers and my fingers are pointing towards the screen, they are moving into the screen. As you people are able to see, they are moving towards you. You are appearing to me in the screen. So it is inwards. That's why A is inwards. For inwards, you have a cross. Remember these symbols, cross and dot, they will show you your direction of magnetic field, because writing all the time into the page and out of the page is not possible. So this will be used, inwards and outwards, dot and crosses will be used. And see, for this B point, if I use, for B point, if I use, this is the downwards direction that is flowing. Now this is, my point is over here, B point. So they are pointing towards me. This, my fingers are pointing towards me. Away from you people, means away from the screen. So this shows that it is outwards. And for outwards, we show it by a dot. Clear like this. Rest of the methods, I'll let you know. First, note it down till here. So this you have written no from vector form. Yeah. And if you still have doubts in the directions, just ask me. One more method we'll discuss before moving on to the numericals. This is one method, another method we have. Right hand only will be used. So right hand thumb rule is there, but one more method we'll see. See the next method first. I'll write down the writing portion as well, but first let us study what is this. Now see, in this, what we have to do, in this method one, what did we study? We pointed our thumb in the direction of current and the curvatures of fingers gave us the direction of magnetism. Now place your fingers, all your 4 fingers in the direction of current. Like for me, if in front of me, this first example. This one. The fingers are, I am pointing my fingers towards this direction. Now I have to curl my fingers, or I have to curl my fingers towards the position vector that is given. Like A point is mentioned, so I have to curl my fingers pointing towards them. So if I keep my palm like this and my point A is this, in front of me right now, A point is appearing like this and this is my palm. So my fingers are pointing towards the direction of current. If I point like this, so my fingers are moving not towards A point, they are moving towards the screen. Now let me shift it. If I keep my palm like this and now I curl my fingers, now my fingers are curling towards this point. So now the direction of thumb gives you the current. See, the thumb is pointing towards me. That is outwards for this A point. So this is also a method that you people can use, whichever method suits you. I'll repeat this one. Let's see this one. First example, B point. Fingers are here. B point is here. All right, this is my B point. If I curl my fingers like this, then the direction of fingers pointing is not towards the position vector. If I point my fingers like this is not again. If I point my fingers towards myself, they are also not giving the direction. Now, if I point my fingers like this and then I curl it, now they are getting curled towards the point B. And this shows the direction of the thumb gives you the direction of the magnetic field. And see, this is leading towards the screen. It means inwards. And that was correct that we had seen. So I'm writing down the statement and then try with the same rule. Okay, note down the statement, try for both these parts. I'll do it again and check whether you're getting the same answer or not. All right, let me write down this first. So this is method 2. It says what? This is also right hand thumb rule only. Place your fingers along the direction of current. And curl it. Curl it towards R. Towards R means whatever point is given. Towards R, or let me write point, whatever point you have chosen. Then the thumb gives the direction. Then the thumb gives the direction of magnetic field. All right, now I am giving you again example. So note down this as well and try this. This is the direction of current at this point A and this point B, and this is example 1, this is example 2, this is A point, this is B point. Right. First tell me for example, and whenever you're answering, if you're answering for both the parts, so tell example 1 A, B, example 2 A, B, but using this. No, Fatima and Sarah answers are incorrect. Try once again. Krishna, for first part it's correct. Try for the second part. Yes, Fatma, it's correct. Now it's correct. Example 1. This is given by. Okay, Krishna, you have answered for the second one. No, okay, for the second one, it will be yes, right? Example 1, Hamza, right? 1 towards A. A is the point given to you, Sarah. Fatima, second part is also right. Example 2 is correct. Fatima and Krishna. Example 2 is correct. Kulsum, example 1 correct. Yes. Kulsum, second, yes, second part is also right. Now see, for all those who are not able to do, this was the direction of current flowing. For me, it's pointing for all of us. In the screen, if it's same for all of us, it is towards the right hand. For example 2. Example 2, yes, answer, right. So see, this is pointing towards the right hand side. Now I am keeping my hand like this. If I curl my fingers like this, I do not have the point. Point A is where? Point A is on the top of it. So if I curl my fingers towards A, thumb is where? Thumb is pointing towards me. Towards me means what? Outside of the page. So this point, this becomes outwards. And B, see, if I keep it like this, and this is my point B here. If I curl it, my fingers are not pointing towards B. If I place it like this and I then curl it towards, this is now pointing towards B. This is leading in the inwards direction. So this is represented by a cross. Similarly, for the second example, now the direction of current is like this. A point is where? A point is on the top. So if I curl it like this won't be the solution. Now if I keep it like this, and this is my point, and now if I curl it, this will lead me towards you. You people are on the screen. It means inside the page. That means in words. For the B point is below it, like this. Here is the B point. Now, if I curl my fingers towards B point, my thumb is pointing towards me. Me means outwards. So this gives the direction outwards. All right. Now, in your vector form, your cross product and dot product will be utilized. But in your vector form of your Biot law, no, then your cross product will be utilized. So all of you revise cross product. Let me just discuss cross product briefly as well. You people, we have discussed cross product as well when we were discussing torque. Remember, we had discussed PE sine theta was torque. So just make a note point in your registers and write about cross product. First, let us discuss, then you people can write. If two vectors are there, vector A is there, vector B is there, both are making an angle of theta, then cross product of A and B, this is given by magnitude of A, magnitude of B, and sine theta. Now, how to write their directions or how to choose it? It's better if you write I cap, J cap, K cap. For all those who forget whether it's K cap cross J cap that gives minus I cap or plus I cap, it's better if you write this in this way, I, J, K. And then for clockwise, take it as positive, and for anti-clockwise, take this as negative. Means let's start moving clockwise. I to j. So I cap cross j cap gives you leftover is k cap. And sign, since we are moving clockwise, it will be positive. Now let's move clockwise from j to k. J cap cross k cap. What is left? Third one, I cap is left. Sign, since we are moving clockwise, it will be positive. Now k cap cross I cap. Whatever is left, j cap. So this will be positive. Now let's move opposite. If you move from j cap to I cap, j cap cross I cap, it will give the third one, that is k cap. And what do we choose? We choose negative sign for anti-clockwise. Then moving from I cap to k cap, I cap cross k cap. This gives you whatever is left, third one, j cap. Since it is anti-clockwise, put a negative sign. And then similarly from k cap to j cap, k cross j, this will give you I cap, but with a negative sign. Just make a note point and just write it down. So and text me when you people have written. Write me in the chat box. So I'll stop it till here only. Krishna, Sarah, done. About others. Okay, Atif is also done. Atif, Sarah, and Krishna. Okay. Others done? Fatma. Okay, so most of you have written it down. So all those who have done, you can leave the class. We are stopping it till here. So from the next class, we'll continue. All right. Okay, take care. Bye bye.
Thank you, teacher.
Thank you, ma'am.
Thank you, ma'am.
Thank you, ma'am.
Okay.